Sulfuric acid or H2SO4 corrosion, understanding the effects of acid on materials. Overview of sulfuric acid corrosion. Sulfuric acid or H2SO4 is one of the most corrosive substances encountered in industrial environments, posing significant risks to both equipment and human safety. Its corrosive nature stems from its strong dehydrating and oxidizing properties, which can damage metals and organic tissues. The severity of corrosion depends on several factors, including acid concentration, temperature, and the type of material exposed. In industrial settings, sulfuric acid is commonly found in alkylation units, wastewater treatment facilities, and drainage systems. It can also form from sulfur trioxide or SO3 and water at lower temperatures, creating highly corrosive conditions in gas analysis systems and other processes. Beyond industrial applications, sulfuric acid is present in everyday products such as drain cleaners and battery acid, which also pose hazards. Understanding its behavior and mechanisms is critical for designing safe processes and selecting appropriate materials to prevent catastrophic failures and injuries. Mechanisms of sulfuric acid corrosion, dehydration and oxidizing or reducing actions. Sulfuric acid exhibits multiple corrosion mechanisms that vary with concentration and environmental conditions. At high concentrations, H2SO4 acts as a powerful dehydrating agent, pulling water from organic tissues and materials, which leads to severe burns and charring when in contact with human skin. This same property can degrade certain materials by removing moisture, weakening structural integrity. In terms of chemical action, sulfuric acid behaves differently depending on its concentration. At concentrations below 70%, it acts as a reducing acid, attacking steel and alloys through electrochemical reactions. At concentrations above 70%, it becomes a strong oxidizing agent, aggressively corroding metals and accelerating material degradation. Electrochemical effects also play a role, as corrosion rates increase with acid concentration due to reduced polarization resistance on metal surfaces. These combined mechanisms make sulfuric acid a complex and dangerous corrosive agent requiring specialized handling and mitigation strategies. Industrial processes and risks, applications and vulnerable areas. Sulfuric acid corrosion is a major concern in various industrial processes. Chemical plants, particularly alkylation units and reactor effluent lines, frequently encounter sulfuric acid exposure, leading to equipment degradation. Storage facilities for sulfuric acid also require careful design to prevent leaks and corrosion. Wastewater treatment plants face constant exposure to acidic environments in neutralization pits and drainage systems, where sulfuric acid can accelerate material deterioration. In gas analysis systems, such as continuous emission monitoring systems or CMS, sulfur trioxide or SO3 converts to sulfuric acid mist as hot gases cool, causing downstream corrosion in probes and chillers. Even in everyday applications, such as drain cleaners and battery acid, sulfuric acid poses significant risks to plumbing systems and personal safety. These scenarios highlight the importance of robust material selection, process control, and preventive measures to mitigate the corrosive effects of sulfuric acid in industrial and domestic environments. Corrosion effects, impact on metals and human tissue. Sulfuric acid corrosion can cause severe damage to both metals and human tissue. On metals, it leads to general or localized corrosion, compromising equipment integrity and potentially causing leaks or catastrophic failures. The electrochemical nature of the corrosion process accelerates metal loss, especially in environments with high acid concentration and elevated temperatures. For human tissue, sulfuric acid exposure results in severe chemical burns due to its dehydrating and oxidizing properties. Contact with skin can cause charring and permanent scarring, while exposure to eyes may lead to blindness. Ingestion of sulfuric acid is life-threatening, causing internal burns and organ damage. These effects underscore the dual hazard posed by sulfuric acid. It is not only a threat to industrial equipment but also a serious safety risk for personnel. Proper protective measures, including personal protective equipment, PPE, and emergency response protocols, are essential in environments where sulfuric acid is present. Prevention and management strategies for mitigation. Effective prevention and management of sulfuric acid corrosion require a combination of material selection, process control, and containment strategies. Choosing corrosion-resistant materials such as zirconium, tantalum, and hastelloy, or applying specialized linings, can significantly reduce the risk of equipment failure. Temperature control is critical to prevent the formation of sulfuric acid mist, which can occur when sulfur trioxide reacts with water at lower temperatures. Secondary containment systems should be implemented to manage spills and prevent environmental contamination. Proper design of drainage systems is also essential to handle acidic effluents safely. Neutralization of acidic waste streams before disposal helps minimize downstream corrosion and environmental hazards. Additionally, regular monitoring and maintenance programs, including inspections and predictive tools, ensure early detection of corrosion issues. These measures collectively help mitigate the risks associated with sulfuric acid corrosion, protecting both equipment and personnel in industrial settings. Summary and key takeaways. Sulfuric acid corrosion is a complex and dangerous phenomenon that affects a wide range of industrial processes and poses significant safety risks. Its dual action as a dehydrating and oxidizing agent makes it highly aggressive toward metals and organic tissues. The severity of corrosion depends on factors such as acid concentration, temperature, and material type, requiring careful consideration in process design and material selection. Industrial sectors like chemical plants, wastewater treatment facilities, and gas analysis systems are particularly vulnerable to sulfuric acid corrosion. Preventive measures, including the use of resistant alloys, temperature management, containment systems, and neutralization strategies, are essential to mitigate these risks. Understanding the mechanisms and effects of sulfuric acid corrosion enables industries to implement effective control measures, ensuring operational safety and equipment longevity. Ultimately, proactive management of sulfuric acid corrosion is critical for maintaining reliability and protecting human health in environments where this powerful acid is present.